So, of course, the name of the class is Introduction to PLCs, ILT 194. So, what is a PLC? A programmable logic controller. Everybody know what that is? Anybody know? Have y'all heard of them before? Well, basically, a PLC is a computer that's specifically designed to run machines. And of course, one big advantage of it, when it originally came out, it was, we'll show y'all some what we call relay logic, or relays, how relays work. Basically, what it was, in a control system, what has been proven over time in very complicated control systems, 90% of the system is decision making. Did this happen before that? Did this happen after that? Is this true or this is false? We used to do all that logic with relays. So logic has been around for years, long before we even came up with computers. Then they realized that relays, these are what we call hardwired circuits. These are actually physical circuits that's wired up. And 90% of the control was actually, of the logic was just controlling when things happen. Well, what they realized is that control could be programmed into a computer, which is what a PLC does. So a PLC can't run a motor, but a PLC can bring in a relay that runs a motor, if that makes sense. But it's that 90% of the control logic that the PLC can come in and take the place of. So instead of me coming here and wiring up, when I went to work at U.S. Steel, most of the logic was actually relay logic. And they had a line out there we called the galvanizing line, and it was the line that actually put the zinc plating on straps that you see on corrugated roofs and stuff like that. And they had three relay. They had the line divided into three sections, and each section had its own control house. And inside that, there must have been 500-600 relays inside there, just to control that section of the line, just to make sure that this happened before that. They came in and replaced them with one PLC. And now you go in these big old houses and you got one PLC in there, where you used to have 500 relays. So that's the big thing. And what's nice about a computer is a computer is what we call reprogrammable. So if I needed to change a hardwired circuit, what would I have to go out there and do? Rewire it. In fact, when they first started doing cars, they used to have two production lines. One line they was rewiring for next year's models, and then they were running this line because they had to do so much hard wiring and rewiring. Now they might be down for 3 weeks going from different models, because now they use everything that's programmable. So they just go out there and do what? Put a new program into these computers, and now it's up and running. So first of all, these guys replace electrical circuits, so we need to know what an electrical circuit is. So y'all write this down. See if y'all can write the answers down. All you know, we're going to go through all this, but on your sheet of paper, write it down and see if you can know what these are. Oh yeah, it's back on one of the tables. Got an electric one. We're uptown now. So just write your answer. You don't have to write the question. Like I said, we're going to go. Are we okay? All right, I'm going to move on. So yeah, let's see. I'm sorry. Somebody got to say, what is a programmable controller? What is an electrical circuit? What is an electrical conductor? What's an insulator? What's the natural metal? Which natural metal is the best conductor of electricity? What are the two most often used conductors? What's voltage, current, resistance, and power? And what's the difference between direct current and alternating current? What is the cycle of hertz, the frequency of hertz? And what is electrical open and short? We're going to see some additions in this. What is required for a basic electrical circuit? What is the difference between series parallel and series parallel circuits? What's the difference between resistance and reactance? A lot of y'all probably don't know this. And true power and apparent power. This is what we're going to talk about. They'll give you a shot. I've got about 5 minutes. Pause the lecture. And it's not important if you get all of them. So what we look at, so what's a conductor? What makes a device a conductor? Of course, most of y'all know that most metals are pretty good conductors, right? So of the known metals, which one is the best conductor of electricity? Silver. By far. Followed very closely by copper. Followed by gold, aluminum, and then all these other guys that we don't use. We do use some tin as a plating, but we don't use it as a conductor. So silver is the best known natural conductor of electricity. Well, we don't use much of it now. Why?
It costs.
Yeah, very cost. We do use it as what we call a plating. We have what we call contacts. Contacts is where we come in and we make a connection simply by just touching two conductors together. So right there, when it makes that touching, we want that to have very low opposition. So a lot of times they'll go play contact switches, so light switches. If you ever tore a light switch apart and look where it actually touches the other side, you'll probably see it's got a little silver coating on it. We do use gold as a plating. What advantage does gold have over most metals? Huh?
Last one.
Because why? What happens to most metals when we expose them to the atmosphere? They corrode. We call it oxidation, or they oxidize. The Statue of Liberty is made out of copper. What color is the Statue of Liberty? Green. Why? Because it's oxidized, is coated, and copper oxide is a pretty good. It opposes current flow. Gold, guys, we don't understand how slow gold rusts. I mean, they pull gold up out of the ocean that's in salt water, which is an oxidant, right? You'll understand that. And it's still what? They knock off the barnacles and it's still gold. It still looks like the day it was minted. So we use gold for a lot of plating. This is becoming popular. We're starting to move down to this. Tin has a very low oxidation rate too. Used to, when you got inside computers, you saw gold all over the place. It wasn't, the conductors were copper, but they plated them with gold. All your connections and stuff. You can go down to Walmart and you can find an HDMI cable, and they got the ones that's gold plated and they got the one that's tin plated. And people will pay $50 for the gold plated one. These are here. So this is the best conductor of electricity. And here they are in the chart. So the two most widely used, guys, is copper. And then the next most widely used is aluminum. Now look at aluminum. Well, what we use, and we'll look at that in a minute, we use aluminum for what we call our high voltage lines. And we'll look at why here before long. So we can use aluminum as long as we transmit the power at extremely high voltage. Now, the problem with extremely high voltages is they're very, very dangerous, right? So all your, what we call high tension or high voltage lines that Alabama transmits power, those are going to be made out of aluminum. And then when they get down to our telephone poles, even though it looks like they're silver, they are actually copper. We use a lot of copper when we do them. So what's nice about aluminum is, number one, it's a lot cheaper, right? You understand? Readily available, a lot cheaper. Plus, it's a lot lighter, so when I build these big towers that support all this wire, they don't have to be as big because aluminum doesn't weigh anything. And here they are. inside the, what we call the periodic table. And here they are. Here's the guy. And here's the one over here by itself. Aluminum is almost an insulator. What makes it a conductor, by the way, is that we know, everybody understands what's the makeup of an atom. First we have a nucleus, and what's spinning around? Electron. And we know that it moves in shells. The first shell has to have one or two, but after that, the outside shell can have a minimum of 8 or a maximum of 1. And that's what determines that outside shell. We call it the valence shell. This determines whether it's a conductor. And that's what this little number, y'all can see this right here. This is the valence shell right here. It's got 1. This has got 1. This has got 1. And this has got 1. So anything that's got 1 electron out in the valence shell makes it a really good conductor. Anything that's got 8, which would be over here, these make what we call really good insulators. And then we have anything that's got 4, we call it semiconductor. Aluminum's got 3, so it's almost a semiconductor. So, but we still can use it, even though it's got more opposition. We still use it, but we do it extremely opposite. So silver, most commonly used. Copper, extremely good. Gold, commonly used in the plate. Aluminum, commonly used for high voltage electrical conductor. Copper and aluminum are probably the most widely used. We use aluminum for a lot of transmission. Integrated circuits use aluminum for the conductors for years because copper and silicon would actually diffuse inside each other. So what they did, and that limited the speed of all our processors for quite a few years because they had to use aluminum, and aluminum's got a pretty good resistance. Finally, Intel came up with a method they could coat the copper. I don't know if y'all remember a processor called Coppermine. So they came up with a method where they could marry copper with silicon. So this is what we're going to deal with, force. What is a force? These are physics definitions. So it's an interaction that attempts to change. By the way, all these PowerPoints are up in Blackboard under course content, lecture slides. It's an interaction that attempts to change the motion of an object. Work is the transfer of energy from one physical system to another, especially the transfer of energy to a body by an application of the force moves the body's direction. Joules, ergs, and foot pounds. Power, we're concerned with force and power. Now, what is power? It's a rate of doing it. So that means I can say it in this, we talk about burning calories, right? Well, calories is, we have to do work to burn calories. So I can sit in this chair all day long, or if I could get up and run, which one would we do? Because now we're doing what? It's the rate of doing work. Force times we can do what? Force divided by distance. Right? You understand that? This would give us work. So the shorter the distance, you're generating so much force, the shorter the distance, the more work you bring. So that's like people walking, you know, so if you walk for 1 mile and you run for 1 mile, which one's going to do the most work? One that runs, because of this guy right here. It's how much force you put in time to walk. Speed. So distance goes up, speed goes down. This is the guy that we use there. Force times speed. So when we calculate electrical work, this is the guy that we use. So what do you pay? What do you pay every month? If you pay bills, when you pay for your electricity, what do you pay? You pay a power bill. So you pay for power. And so how do they calculate power? But how do they calculate it? That's what it's in. This guy here, force times what? Speed. That's what they use to calculate power. All electrical devices operates from electrical current. The amount of power produced by these devices is determined by the amount of current. So what we're going to do is we're going to push something. And what we push, we call it current. So before anything moves, we got to have force, right? Understand that. Very okay. Now electricity, this force is what we call voltage. Voltage does not move. Voltage is just a what? A force or a push that causes something to move. Now what is causing it to move is it's causing it to move something called current. So if I know the amount of current, the speed of the current, and I know the amount of force, then we can calculate the work. Makes sense? The amount of current flows through them, and the force is the cause of the current flow. The amount of current is controlled by the amount of force divided by the amount of opposition of the. So to do work, we got to have a force. We can't generate a force unless we push something, right? You don't understand that. So to do work, we got to have an opposition. So every circuit has some type of load. Everybody understand? Got some type of opposition, and the opposition is what's doing the work. That makes sense? Okay, so far. Electrical current. So what are we pushing? So your voltage source, like your car battery, it does not create current. It does not create it. It just causes what's there to do what? Move. It's just like saying a pump creates water. A pump does not create water. What does a pump do? Moves water. Okay. So what we do is we move electrons. So we got all these atoms that's already out there that we want devices that can give them up freely. And that's what conductors do. And then we cause a difference of potential. So that's all voltage is. It's just a difference of pressure. And if we put a difference of pressure beside something, we generate a force, which if something can move, it's going to do what? It's going to move. So that's what's moving. These electrons are what's moving. So the force would be what we call the voltage. We have two voltages available in our house. What's the two voltages available in our house? Yeah, 120 and 240. That don't move. All it does is we apply a force, and then all the electrons that has the ability to move, that's what causes them to move. Everybody understand that? That makes sense? So it's called an electromotive force. So a lot of books teach it as EMF. And in some books call this voltage. Electrical current consists of an atom of electrons that have been forced to move by a difference of electrical potential. And we call this voltage, or it's also called electromotive force. Everybody okay? The strength of the difference of electrical potential and the amount of opposition. So we can't create work without opposition. Everybody understand that? Okay. So we got to push this against something. So this light bulb right here is an opposition. So it's got an opposition. Basically, we push current through that, and then it does work. Now, what work do we see here? We see light, right? You understand? We got heat. We got motors that turn. We got all these kind of stuff. And that's caused, we can't have force. We can't have current without a force, right? You understand that? And then what's it causing to move? It's causing these electrons to move, which we call what? So what determines how fast the electron moves is how much force we have, right? And how much opposition we're trying to push that through. That makes sense? Your question so far? Austin, back? Some materials such as, but the problem is that I'm a opposition. So literally I can take a 9-volt battery and I can push this finger on top of one side and put this finger on top, and I'm a circuit, and there's current flow through my body, and it does work. You don't understand that? A lot of people, you'll see, I do that all the time too. Check a 9-volt battery, they check a 9-volt battery facing to the tongue. But you can actually feel the work in your tongue, right? You understand that? So, anytime you get across, of course, the electron flow, I have a lot of opposition. And the problem with the human body is that we have really no idea exactly what opposition it has at any one time. You sweat a lot. Salt water is a pretty good conductor. So if you're really, really sweating a lot, then you have a low opposition. Some people, I felt the car battery. Car battery is only 12 volts, but I felt current from a car battery because I got across the terminals when it was really, really hot. If you got any cuts on your skin is is your insulator. Your meat inside there is a pretty good conductor. We're carbon-based life form. So, you got to be real careful about cuts on your fingers. So, push, of course it's hard to say, but what the National Fire Protection Association, NAFTA, they have a safety standard called 70E. They consider anything above 50 volts of push to be potentially lethal for us. It don't mean you can't get killed for anything less, but that's what they do. And that's when you have to start wearing a lot of safety stuff. We call it PPE. Anybody know what PPE stands for? Personal protection equipment. Some materials, but I've got to keep this push. So we got these copper wires up there, and they don't have any opposition at all. I've got to keep that push and that current flow inside those conductors, right? And I've got to be able to handle those things. I got to be able to put them together so they don't touch. So we have some materials that have a really high opposition to the current flow. There's no such thing that has infinite opposition to current flow. And if you put voltage across a path, and you're going to have current flow through it. So even insulators have current flow through it. It's just that it's so small and it doesn't affect anybody, right? You understand that? It's called volumetric current. Some materials such as metals allows electrons to move freely, while others such as rubbers, Teflons, all these different types of things, ceramics. For this reason, most metals make good electrical conductors. And rubber, paper, ceramic, glass, Teflon, these make good what we call insulators. So just about all your conductors are going to be, any conductor that I can get around is going to have an insulator around. Right, you understand? If the voltage is high. Air is a pretty good insulator, so Alabama Power uses a lot of air as an insulator. If you look at the power lines, they're not coated with anything except a little copper oxide. So EMF or voltage is the difference in electric potential that forces electrons to move if there's a path, right? Current is the flow of electron that is the result of a difference in electric potential. And then resistance. We have two types of opposition. When you take DC, you take intro, you'll learn about this guy right here. Later on, we'll have to introduce this. We probably might not talk about it much in this class. But resistance is an opposition that doesn't change with frequency. We'll talk about that a little bit. And reactance varies with frequency. And like I said, we'll look at that later on. Everybody okay so far? So basic electrical circuit. So we have what we call an electrical circuit. So electrical circuit is a complete path for current flow. A basic circuit consists of a voltage source. We've got to have push, right? You understand that? Then we got to have something to move the piping. Everybody understand pipes, right? You understand that? What do we use pipes for? For what? So the pipes themselves. So we use electrical conductors. That's what we're moving the current from. So electrical circuit, we have to have a voltage source. We have to have a conductor. And that's all it is with the pipe. It carries. So conductors have one function in life, and that's to get the current to the load. You don't understand that? That's all it's for. It's just like the load does the work in the circuit. So we got to have a source conductor, we have to have a load conductor, and we have to have a load. A load is the device that does the work in the circuit. Everybody okay? Everybody okay? Most electrical circuits also consist of a control device. Perfect example of a control device is that light switch on the wall. Like that. What can I do with that light switch? I can turn the lights off or I can turn the lights on. Everybody okay? So here we're going to deal with a lot of different control devices, different things. And we'll also make a trip over to the mechatronics lab and actually look PLCs actually in action over there. So a good analogy of an electrical circuit is a unit control system. Everybody pretty much well knows how that works. So how does that work? So what do we got? What creates our difference in potential? Your heart. Okay. What does the work? What's the load? Where does the blood go? Goes to your organs, all your muscles, all your organs, right? So that's your loads. How do we get it from, the heart does not make blood, right? It does just what? Moves it, right? You understand that? Moves it. How does it get from the heart to the load? Two blood vessels. Our arteries take it out, veins bring it back, right? You understand that? Okay. That's an electric circuit. The heart creates a difference in pressure. That pumps blood through arteries, through the muscle, pulls it back through our vein. So we know the voltage source is similar to the what? Heart. Electrical current is similar to the what? Blood flow, right? Electrical conductors are similar to the what? Everybody okay? So this is a basic circuit. Very basic circuit. So we have a switch up here. Here's our control device. It's showing the blue lines. These are actually indicating the current flow. We have a symbol for a DC. This is a symbol for a direct current voltage source. Originally it was a symbol for a battery, but it's all your DC voltage sources have that symbol. This will be the source conductor right here. So this is what's actually pushing the electrons. Once it goes to the load, then the positive polarity pulls it back, right? You understand? And then, of course, when I close the switch, the light comes on. So there's the source conductor. Here's the load. Here's the return conductor. And there's the controller. But we don't see very many circuits without a control device. Of course, that's the symbol of the switch. This is the symbol of a light bulb. So what we do is we have drawings. This is what we're going to have to learn. It's just like a road map. What does a road map use? Or your GPS. Your GPS even uses that. It uses symbols, right? And you learn what these symbols are for your road map, right? You got a symbol for an airport. You got a symbol for a park. You got a symbol for this. We don't actually draw the pictures. We use symbols, and it allows us to reduce that down to a little old tiny screen instead of trying to actually draw the physical road and the physical McDonald's and all that other kind of place, right? They even use it on the interstate. We use symbols. We have symbols for stop signs. We have symbols for cautions. We have symbols for all kind of stuff, right? Everybody okay? So we can take those loads and we can hook it three different ways. We can hook the loads in series. We call this a series circuit. We have a parallel circuit, and we have series. You don't use these guys right here in controls. With PLCs, we're not going to have any series parallel circuits. All we're going to have, they're going to be single element series circuits. They're going to be basic circuits, or they're going to be parallel circuits. This is how we hook the loads. It has nothing to do how we hook the control devices. That gets people confused. So in a series circuit, consists of one or more loads. The only thing we're going to do is have one load. We're not going to have more. We're going to have one load, or we're going to have a parallel circuit. The voltage provided by the source is distributed across the load proportional to loads off the grid. By the way, in electricity, somebody tell me what we represent opposition in. Anybody know? Somebody else already had classes. Starts with an O. It's a unit called the ohm. And we use the Greek symbol most of the time for omega. So that's a symbol right there. That's a symbol right there. That's a symbol. But what does that symbol tell you to do? Well, it depends on where you're at. So we use that symbol. We use that symbol several times. In logic, it means it's an OR logic. In math, it means it's add. In universal serial bus or USB, it means it's the uninverted signal. So that's a symbol, but a symbol is when we use what? When we use a picture or basically a graphical thing to represent something else, right? You understand? So we're going to have to learn a lot of symbols. Since there's only one path current flow through, all the loads are exactly the same. So this would be an example of a series circuit. And we're not going to run into these. And when you take DC, most of y'all will take that class. You're going to have a multi-load series circuit. And PLCs and also motor control, the relay or motor control, which basically is relay. So we have what we call logic. Anybody know what logic is? And so we have 5 basic functions, believe it or not. We have and, we have or, we have NAND, we have NOR, we have NOT. And then we combine those to get more complicated functions. Okay. So we can combine them to get exclusive ORs, exclusive NORs. We can do counters, we can do latches, we can do all kinds of things. So in the series circuit, so relay logic. So what we're going to be doing is we're going to learn logic. So if you didn't, some people answered that question, but if you don't know it, you're okay. We're going to teach you logic. And we call these they call it ladder logic or relay logic. So for years we used these big mechanical devices, electromechanical devices called relays. This is a relay, and what we do is we use a magnetic field to cause a unit to move, and you can manually force this. And all it does is close contact to make circuits. So this would be a control device, and we did logic with this. We can do AND, we can do ORs, we can do NAND, we can do NORs, we can do exclusive ORs, exclusive NORs, but that's about it as far as logic goes. These guys, look at this. And plus their electromechanical devices. Your car is an electromechanical device, which means what? When it fails, 2 things can fail. They can fail mechanically, or they can fail electronically. And that's the problem we have with relays, is that they do a lot of work, and then these guys here fail because they're electromechanical devices. By the way, this is what we call a manual override right here. So you can literally make this work. And if you're out in the field and you see a manual override, don't say, let's see what this will do, because you could kill somebody with it. So the only thing we're going to run into in PLCs and also in relay logic, true relay logic, if you take motor controls, is one load. We're not going to have multiple loads. But the way this works, the voltage. So what happens anytime? What's one of the first things when you go into the doctor? What's one of the first things they do? Anytime you go for a doctor's visit, check your pressure. Right? You'll understand that. Check your pressure. Because if you start getting clogged and stuff in your blood veins, then you're adding opposition in there, right? You understand that? So what happens is that every time we go through a load in a series circuit, we lose pressure. pressure is not moving, it's just that we lose pressure because we've gone through an opposition, right? In electricity, we call it a voltage drop. Well, anytime we go through an opposition, there's a voltage drop. Now, this is the way it would work. So if this had 1 ohm, this had 2 ohms, this had 3 ohms, and this had 4 ohms. If I add those together, I get what? 10. Well, if I had 10 volts over here pushing this, then this guy right here would lose 1/10 of the volt. So that means if I had the ability to measure the voltage right here, it would be 9 volts. This right here would lose 2/10 of the volts, which would be what? 1/5. So that guy right there would drop 1/5. This guy right here would drop 3/10 of the volts. This guy right here would drop 4/10, which would be what? 2/5. So in a series circuit, the load that has if they all have exactly the same opposition, then they would drop the exact same voltage. Now, where do you run into these guys at? We got a holiday coming up in December. We call it Christmas, and everybody puts up Christmas lights. That is a series parallel circuit. Now, what happens is every one of those are exactly the same size. They got the same opposition. So if I've got 18 of those out there, and I've got it on 20 volts, then each one of them will drop 1/18 of the volts, right? I'm sorry, if they got the same opposition. So that means I can use smaller bulbs, and they don't have to be rated at 120 volts. But what happens if one of them blows? What happens? Now you lose all of them in that string, right? Because there's only one path for current, right? So what you did, you created what we call an open. So these guys we run into them a lot in electronics. We don't run into these guys in multiple loads in our class. We don't have how many loads? We're either going to have one load or we're going to be parallel. So we have parallel circuits and we have one load series. Because if you put 2, then the voltages would be divided out, right? And then the power would be divided out, and that causes big problems. Works great for in electronics and stereos and stuff like that, and light and Christmas lights. So that's the path for current flow. Now, parallel circuit. This is the guy there. So your house is wired. Your house is a parallel circuit. So the voltage applied to each load is the same. All loads are connected across the voltage source. The current is distributed inversely proportional to the current opposition. So this is a parallel circuit. So if I've got a 120 volt source, and if I was to measure the push across each one of these, it would measure 120 volts. Now, what's the advantage of parallel circuit?
One load goes out, the rest of them don't.
Yeah, so we can turn lights off in the house that don't affect any other lights, right? You understand? We can add loads, we can take loads away, right? And it doesn't affect the other loads. The power grid is a parallel circuit. And of course, your house is wired parallel. So we're going to run into parallel circuits. It allows us to use multiple loads. Are we okay here? So I can open circuits. I can open this guy. I can open this guy. If I wanted to turn the whole thing off, I would put it up here. What usually goes up there, does? It's a device called OCPD. I don't know what that stands for. Has this symbol right here. Yeah, good. It's called a circuit breaker or fuse. So this is a switch, but it automatically activates and opens the circuit, right? So there's no current flow if it senses overcurrent. So everybody's seen a circuit breaker. We call them, we say they pop, right? And fuses. So these are overcurrent protection devices. There are parallel circuits in both relay and PLC logic. So this would be a series parallel. We're not going to have any series parallel circuits, but we'll just look at them. So this would be an example of a series parallel circuit. Just about all electronic circuits are this. If I was to pair, if I had the diagram of my cell phone, this is the guys it's going to be. It's going to be a series parallel circuit. But we have no series parallel circuits in relay or PLC logic. Control devices. Now we do have a lot of control devices. You walk into a plant, you're going to see all type of control. Push buttons, switches, HMI panel, human machine interface panels. You'll see a bunch of those now. We're not going to use HMI panels in this class. If you take the PLC 3 class, you might get into that. But they basically uses some type of touch screen that simulates push buttons and stuff like that. Controls the flow of current produced by the electrical power supply. The connections of the control devices does not determine if it's a series, a parallel, or a series parallel circuit. That is how you connect the load. So we can connect control devices all different ways. We'll connect them in series, we'll connect them in series parallel, and it doesn't turn it into a parallel circuit, right? Y'all understand that? Control devices can be connected in series parallel or series parallel. Some control devices include switches, push buttons, relays, and then what we call sensors, electrical sensors. So what is your sensor do? So we got sensors all in our body. What does our sensor do? Your brain has no idea what touch is. What does your brain process? What does it process? Electrical impulses, right? So that's what your brain processes. It processes electrical impulses. So we got all these nerves, all these sensors out there. What do the sensors do? Takes a physical stimulus and converts it over into a what? Electrical stimulus so your brain can process it. That's what we do. We use sensors. We have sensors in, so this guy's got a sensor on it. So what can I do with that sensor up there? I can turn the projector off or on. I can bring up a menu. Well, it's got a sensor up there. What does that sensor do, right? It takes one quantity and does what? Converts it over to what? Something else, right? So these are their control devices. We've seen that. So these are control devices. Some of them we all use all the time. Light switches. You got control devices in your car, all over the place in your car, right? One of my doors is not closed, it comes up and says what? You got to yell at the door open, right? You understand that? If you leave your lights on, it beeps at you, you know. My car turns it off automatically after a while, right? Well, now we have auto. We have door sensors on our door, so it knows when it opens, yeah.
Oh, the seat has it too. Right.
Seat's got it to make sure you got your seatbelt on, yeah. And whether it turns on the airbag and that kind of stuff. And all those are doing are taking a physical quantity and converting it into electrical quantity. So the computer, we called it, used to we had one computer. Now we've got two, and from what I understand, they're moving to 3 computers in our car. Right now we have what they call an engine control computer, and we have a body control computer, which basically is controlling your headlights and all your other kinds of things. And they're doing one, I forgot what they call it, but it's an environment control computer. So now we got cars that tells you when you try to get out. We're moving towards self-driving cars, but they keep adding features, right? We got them now that'll slam on your brakes, right? If you're at a certain speed moving through something that's stationary, we got them now that'll stay in the lane for you, right? You understand that, which is pretty good. So we got all these switches. This is a float switch, by the way. These are sensors. We got sensors that'll sense some metal. Y'all probably run across these all day long. These things they mount in the road. That's all it is a metal detector that controls your traffic lights. That's a sensor that senses metals, right? A lot of people think it's weight, but it's not. It's just a metal sensor. That's all it is. Y'all see these metal detectors, these guys, if you go to the beach in the morning, they get out there real early looking for stuff. Well, that's all that's buried out there in the road. It's just a metal detector. We can sense light, we can sense pressure, we can sense sound, we can sense just about anything that we can sense. We can have an electrical sensor that does the same thing. And they do the same thing. In automated systems, by the way, sensors are the name of the game. Because automated systems, what's automation mean, by the way? Do it with little or no human intervention. There's very few that does it with no intervention, but it means, but how does it know when something's there or it's not there, if it's going at the right speed? It's because of these guys called sensors, right? So we're going to learn that that's one of the things we're going to hook up to a PLC is this class we're not going to do wiring. In the PLC 2 class, we're learning how to wire the PLC. Here, this is basically a programming class. We're going to simulate sensors. We're going to use switches or push buttons. Relays. So these are electromechanical devices. PLCs do not replace relays. It replaces the relays that do decisions, right? You understand that? It does not replace the power. So there's no way in the world a PLC would run that motor over there. Cannot run it, but it could pick up one of these guys. These electromechanical switches. So we're going to run it. We still have a lot of relays out there. So normally, control circuits are divided into two circuits. One of them we call the control circuit, and one of them we call the power circuit. And so power circuit, this is where all your big relays are. And these are called solenoids. Symbols of the trade. So what we're going to do when we're going to there's 4 programming lines. So we write programs for a computer, right? And what is a program? That telling it to what to do. You just can't say it's a series. So it's an algorithm. An algorithm is a step-by-step process used to solve a problem. So a recipe would be an algorithm. So, but a program is an algorithm, but an algorithm doesn't have to be a program, right? I'm saying. So a program is a step-by-step process that we tell our computer what we want. So you're looking at a program right now. I'm running on my computer. It's called PowerPoint. It lets me create these slides and it lets me do what? Shows me. This is a program. Somebody wrote this. This thing didn't come up and do it. We write programs in a language. Originally, it was a language that we learned. Rich had called a machine language, and that's the only language the processor really understands. And it is a binary language, right? Ones and zeros. So we call that machine language. You've ever heard people talk about machine language or object code? We don't do that much anymore. What they found out a long time ago is that we can write a program that translates. So everybody understand what is translated? It lets me go to German, right? You understand? And I can talk to somebody that only speaks German if I go to a law. So they're taking my language and converting it over to their language. So that means if we can come up with a machine language program that translates a program written in English into a binary language, then now I can write programs in a language that I understand. The major language that we use in program controllers is a language called ladder logic. And that's what we teach in this class. There's actually 3. We have programmers that come up through programming languages called Pascal and C++. Well, we would like to make a PLC language where these guys could catch on real fast. So we have an STL language, which is a structured text language, where these guys can program PLC. Then we have people that come up through digital, and they learn all these symbols for ands and ors and stuff. Well, we have a programming language called function block programming, which gives these abilities to do what? Program a PLC with very little. And then we have electricians, which have come up through the electrical trade, which is where most people that deal with PLCs, that's what they come up with. And this is called ladder language, and that's what we teach in this class. We teach a language called ladder logic. It is by far the most widely used programming language. There's really nothing that you can't do with ladder that you can do with other ones. So we teach what we call ladder, which is what motor control is. So these are schematic symbols. We already looked at some. These are, this is for a what?
Powerful.
DC power source. This is a symbol for an AC power source. This is the symbol for we call a resistor. This guy has a fixed opposition. We use these guys to control the flow of the current with the values wrong. This is the connection point. By the way, guys, I'm gonna stick around there. If you draw a diagram, and you're gonna draw some diagrams in this class, if you bring two wires together and you don't put a dot, what does that mean? They're not connected, right? This is a device called an inductor. It's really cool. This guy here varies its opposition with frequency. This guy here is called a capacitor. It varies its opposition with frequency. We use these things for filters, all kinds of neat stuff. This is a symbol of a transformer. Now what a transformer does, it works with AC, which we'll look at. It allows us to change the level of voltage between the input and output. This is a symbol for a switch. The symbol for ground. This is probably the most misused symbol in the trade. This is a symbol for a fuse. Mostly. Voltage source, AC voltage source, resistor, connection, inductor, capacitor, transformer, single pole double throw switch. We'll talk about this later on. We need to understand this too. This is a ground. And this is a fuse. These are some of the symbols that we're going to use. We're not going to use a symbol circuit breaker. We are going to use a symbol for a relay cord. So what we're going to do in this class is we're going to take circuits that was developed under relay logic, and then we're going to modify them to run on a PLC. And then plus, when we hook up the PLC, let me bring this up real quick so that you go. This is actually the connection on how we connect the PLC. No, that's not what I wanted. So this is the diagram you see for a connection of a PLC. Here's the PLC. And this I is an input into the PLC. And this tells us which input it is. And we'll talk about that later on. But here's the actual devices that are actually these guys, these are actually the true electrical symbols. So at PLC, you have to draw these diagrams so people in electrical can understand. So that means you got to learn electrical symbols and you got to learn the symbols that we use in PLC, right? That makes sense? So this is a push button. This is a push button. This is a push button that has the ability to latch. It's got a mushroom head on it, and this is a push button. This is normally open, this is normally closed, and we'll look at that later on. These are sensors. So these are symbols. These tell me that these are actually sensors. These are magnetic sensors. So they sense the magnetic field. Maybe you know how to wire these up. Well, if I didn't know what that symbol was, I wouldn't be able to
wireless. I would, if I didn't know what that represented, I wouldn't even be able to wire this up, right? That makes sense? Is that okay?
So those are all magnetic sensors. This is a optical sensor. This is a pressure sensor. And then these two right here are magnetic. Now these are control devices. All these are control devices. Right, okay. And then what we do is we have a portal on our PLC that we call an input port. So all your control devices are going to hook up the input. That makes sense? Right, okay. So this is actually a diagram of what a person would use to actually wire these input devices up to the PLC. And we'll look at a basic input on the PLC. These are outputs. So these are outputs. This is a diagram for a Siemens PLC. We're going to be dealing. There's two predominant PLCs. There's a lot of people that make PLCs, a lot of them. But there's two predominant PLCs in the United States. Originally, it was Allen Bradley. Allen Bradley was all over the place. And then you saw a few Siemens PLCs here and there. Since Mercedes has come to town, what they have done is they have brought a bunch of German companies into our service area. Guess where Siemens PLCs are made? In Germany. So we're seeing a big influx of Siemens PLCs. In this class, we're going to teach the Allen Bradley PLC, because that's still the predominant PLC. And then if you want the Siemens, you're going to have to take some more advanced classes. PLC 3 is predominantly Siemens PLC. So here we teach, we'll get a basic touch on Siemens PLC and advanced PLC if you're registered to that class. But this class right here is all Allen Bradley. And it's still the predominant PLC in our area. And what you're going to find, guys, is just like me. The PLCs that I learned how to use are not even around anymore. I learned how to use a Square D PLC, which instead of being programmed on a computer, it had a dedicated terminal. So all the processing power was inside the PLC. But what you'll find out is that once you learn one, it makes it extremely easy to do learn another. And you'll see that when you finally get into the Siemens. The Siemens is probably the most advanced programming software we got. It's really cool. It's called the TIA Portal, for Total Integrated Automation. We're going to use a programming language called RS Logic 500, which is they're replacing it with RS Logic 5000. But what you'll find out is that they're very, very similar. And once you learn one, all you do is, and we're going to try to show you all the difference between the two while we go through here. Allen Bradley calls their outputs O. Siemens calls theirs Q, which I like because what happens is that when you're typing these in, a lot of people will enter an O, a 0 instead of an O. So what Siemens did is they changed it to a Q. These are outputs. So outputs, these are solenoids. I'll show you what a solenoid is. Anybody know what a solenoid is? You see them all the time. A solenoid is anybody know what an actuator is? What's an actuator? Well, it creates a motion from a force. Well, solenoids are what we call linear actuators, which means what's linear? Anybody know what linear means?
Line.
Straight line, right? Yeah. So a solenoid is a linear actuator, which means it only generates force in one direction. And then you have a spring or something that actually brings it back. We use these all the time. The washing machine. So if you got a washing machine, what turns the water off and on?
Yeah.
A solenoid valve. Yeah, so it's got a plunger You put power on it, it jerks it up, lets the water come through. Then, if you got an ice maker, what turns the water off and on? A solenoid, right? If you go to a place and they say buzz me in, what are they buzzing you in with? A solenoid. It's a solenoid up there, and they tell it to pull it up, and it unlocks the door. When I was in the hospital, they had a bunch of doors that was locked off, and the interns or whatever, they would have little key cards they would press, and you hear it buzz, and it would open them up. So these are solenoids. These are controlling what we call directional control valves, and I'll show you those when we go over it. That's the symbol of the light. It's a green light. And these are just more symbols. So if I didn't understand these symbols, this is a symbol for a valve probably. So this is actually controlling the position of a valve. We'll look at some of those when we go look at the line. So we'll go over there. Once we get a feel of basically a PLC and what's going on, then we'll go over to, we got two manufacturing lines over in the Hall building. That's got, one of them runs off of, Siemens 314 PLC. And the other one runs off of Allen Bradley, Micrologic 1500. The PLC class, the PLC 3 class, what we do is we convert the line from Allen Bradley over to Siemens. We'll show you all that. So we got one Siemens over there, which is pretty good. So that class you really learn a lot. So this, if I want to draw an input and I want to draw a light bulb, then I need to know the symbol for a what? A light bulb. If I'm going to draw a push button, I need to know the symbol for a what? Everybody knows what a push button is, right? These are using momentary contact. These are relay contacts. So these are actually switches that's controlled by the relay. So when we pass that relay around, you notice it had switches on top of it. We call those switches contacts. We can talk about those. We have different sensors. We have float switches. We have, don't understand what a float switch is. We got one in your commode, right? It turns the water off and on. We have float switches. We have flow switches. We have pressure switches. We have all types of different sensors. So we'll look at these symbols as we go along. This is what I really wanted to get into. This is a basic ladder diagram. This is what electricians learn to understand. And so this is the first language. When they decided to program, bring out PLC, this is the guide that they decided to program it, because you had all these electricians out there. They were responsible for, now they're responsible for these computers, and they needed to understand the program. So, or they needed to have the ability to program them, right? You understand that? So this makes sense that this right here was the what? The first language that they came out with. They added the structure tech program and the function block program and all that kind of stuff. That was added later on. But this was the first true language. And this is by far the most used language to program PLC. So what we have here is this is but it's what we call normally closed. Now what we mean by normally closed is that switch is made until you come up and push it. So if that's a normally closed, what does this got? This is a normally. This is a relay. It's the circle. This is true on the PLC. So in the PLCs, we're going to simulate a relay. And what symbol are they going to use for our simulated relay? It's going to be a circle, right? That makes sense. These are what we call overloads. We won't have to worry about these. We would on the actual circuit itself when we wired up the motor. In the PLC, though, we don't have overloads. The problem with motors is when you start them, they pull about 6 to 8 times their run current. So if I want to start a motor and I've got an overcurrent protection device if it says it's rated at 5 amps and I put a 5 amp fuse every time I start my motor, it would do what? It'd blow, because that sucker's going to try to pull 30 amps. So what I would have to do is I'd have to fuse it. I'd have to fuse it to let the motor start. Well, the problem is if the motor stalls, it's going to pull the same current. So if the motor doesn't start, or if it stalls, it would sit there and just burn up, and the fuse would never blow, because it's rated to let the motor what? Start. So they had to come up with a method where we had some device that senses over current over time. So we could draw current, we could let it start, but if it tried to pull that 30 amps for 10 seconds, it would kick out the circuit. And this is what overloads do. This is the 3-phase. The actual sensor is out in the power circuit, but this would be the actual what would kick that out. This is the symbol for light bulb. Now, what this does, guys, is this is a relay, and what does a relay do? It controls contacts, right? Now notice this relay has a name. They give it the name what? M, right? That's M. Let's give it the name M. It could, in real life, it could be anything. When we teach this, we usually use one letter. When you get out there in what we call the real world, the Navy used to call it the fleet. And when I was going through all my schools in the Navy, they say, well, when you get out in the fleet, this is what's going on. Here, when you get out into the real world, these guys are going to have longer names. They give you more of an indication of what they do. But what I see is this relay. So what happens, this is my power right here. So this is a series circuit. It's got one load, right? One load series circuit. Everybody see that? Now these are hooked in parallel, but that does not make it a parallel circuit, because these are control devices. Everybody following? Everybody okay so far? Okay. So this is my power. We consider this to be what electricians would call the hot side, and we consider this to be the neutral. And they're called, in this generically, we call it L1 and L2. So that's my power source. My power source is wired across these two. So I come up here and I press it. So right now, this guy, there's no path for current. I don't have a complete path. And this relay right here would be the inside. Everybody okay? Everybody okay? So what happens, this is a normally closed contact. So this guy, we call that energized. So when the relay, we put power across it, that's when you took that thing and you manually pushed it, that's what it does it, but it does it what? Electrically. So if you looked at that thing, wherever it's at, you'll see some of the contacts are closed when you don't push it. Some of them are open when you don't push it. So this is a normally closed contact. So if this guy does not have voltage across it, or it's not energized, then this guy will be closed. This guy right here will be what? Open. Everybody follow this so far? Makes sense. So I'm sitting here, this light is on. What color light it is, we don't know. All we know is the light. So I'm going to come up here and I'm going to press this button, and this is the symbol of a momentary contact button. What does that term right there mean? Momentary contact means it's only true when you do what? When you hold it. So I'm going to push that button. I just push it. It goes down here and touches that. Now it allows my current to flow through here. Hits that. This comes through here, hits that. That relay energizes. Which means it causes all the contacts are going to do what? Shift. They're not going. We can't say they're going to close. They're going to shift. Because some of them are going to be normally closed contacts. Some of them are going to be normally open. This contact closes. This contact will be what? Open. So the light will go on. But as soon as that contact closes, that's going to close this contact right here. I'm going to do it like that, and it comes over here. So what can I do now? I can let go of the button. And I let go of the button. We call this a memory circuit or a sealing circuit, and you run into these guys all the time. So now my path is this way. Right? So it's sealed in. So how do I stop this thing? Yeah, as soon as I hit the stop button, it breaks the current. This guy drops out. This contact right here pops out. This will close and turn the light. This is relay light. This is called a memory circuit. Everybody okay? Y'all lose anybody? We can take this and program it into the PLC. Very easy. So this will be one of the first circuits that we do. So this is actually, this is actually a ladder logic diagram. This is electrical. This is not PLC. This is electrical. There is no solenoid inside the PLC. But I have a simulated relay that when I simulate it, it could turn on the solenoid would actually be hooked up to the output of the PLC. That makes sense. So here's my power. Here's all these different control devices. Is this a series circuit or a parallel circuit? Series circuit. Parallel circuit. So see this right here. These do not determine if it's, this is what determines. But notice, we come over here, we drop down. So these run off the same L1. And we come over here, so this is a parallel circuit. This control device controls both of the branches. This has individual. Those are all controlled ones. These are all loads. This parallel circuit is easy to see, right? So there you can actually see them connected directly across each other. That makes sense? Well, there's our loads. Well, there's the basic circuit. What do we have? We have a voltage source. Right, you understand. We have conductors. We have a load. And then we have control devices. Controls. Okay, these guys do no work. They don't produce power. They have no opposition. They're just in there. They're not in there to do work. When you think about work, you say, well, they do something. When we're talking about work, we're talking about producing power. They don't produce power. They're not supposed to get hot. So this is why if you got a wall plug in your house that gets hot, then something's wrong, right? If you got a light switch in your house that gets hot, then what? Something's wrong. You need to either replace it. It's got opposition in it when it's not supposed to. So we would figure out which one of these is control devices, and then we would have it. So these are relays. These are lines. And this is just a basic control circuit. How much of these could we hook it, or could we program into a PLC at all things? Now, what's not another thing nice about a PLC is that this is all wire, and you need to make a correction. And by George, you got to go out there and do what? Rewire it. In a PLC, what you think you can do probably 90% of the time. Change the program. We had timers. We had a burnishing wheel on a welder down at Fort Galvin. And they had big old copper wheels, and it was a strip welder, so it actually welded two strips together. And every time it went across and did a weld, it did a resistive weld, and it would come up and it would file it off just a little bit so it wouldn't get enough. Those wheels cost a lot of money. They were solid copper. So if we ran the timers too long, they would burnish off too much copper and they'd have to replace the wheels. If we ran them too short a shorter time, then they didn't burnish all the way around. So, but the problem is that these were dashpot timers. Dashpot timers work off a liquid. Now what happens with most liquids when they get hot and when they get cold? The viscosity changes. So what we would have to do when it turned winter, we'd have to go down there and do what with the time? We'd have to touch them a little bit. When it got summer, we'd go back out there and have to touch them up. And the operator would be out there with a stopwatch. We'd have to set it until it ran around my time. On a PLC, that timer is going to be software. So if I need to change the time, so odds are it's not going to be affected by the what? The weather. If I say 5 seconds, by George, it's going to be 5 seconds, whether it's in December or whether it's in June. Another thing, if I want to change the time, if it's hooked up to a network, these guys now can be networked. They network them all the time. So you can have a guy in Chicago actually playing around with your PLC down here in Alabama. With those features. So this is ladder logic. This is ladder logic. This is motor control. This is residential wiring. I just threw this in here. So this would be what an electrician that needs to wire house needs to look at, and what do they need to do? They need to learn the symbols of the trade. So every one of these is telling that electrician something, right? Y'all understand that? That makes sense. If you didn't know how to read this, you couldn't do what? Well, you could. Yeah. This is an electronic schematic. We're fixing to take it right now. In fact, I think it's will cut out for that. We'll finish it up. This is an electronic schematic, and it's made of nothing but what? Symbols, resistors, transistors, operational amplifiers. And this does not show you how, and what's so funny is you get people in electronics, they want to wire according to the schematic. And when you look at a printed circuit board stuff, it's all over the place. We have this problem in motor controls all the time where they're trying to hook two things together and they're side by side. This is true. And I'll jump on about this. I say you'd never be an electrician, you'll go out of business. So they got a guy right here and a guy right here, and they're right next to each other. And they've got to go back to the power source, and they'll run two wires all the way back to the power source. When all they had to do was what? Run one down and then put a jumper up there. You took motor control, didn't you? I thought you did. So and they'll have wires, big old long wires running over. I said, yeah, it's going to work electrically, but you'll be out of business because you're going to buy all this copper, right? And this guy comes in here, uses half the copper you use, does exactly the same thing because they understand how to. So just because, and the biggest problem we have is people try to wire them according to the diagram instead of trying to figure out which is the shortest path to get from point. So when you look at a circuit board and you look at a schematic or a diagram or ladder diagram is drawn logically so you can figure out how the thing works, right? You understand? So that's what a ladder diagram is. It's logic. It's logically how it's drawn. When you get out in the real world, it's not going to be in the same order. You might have K1 here and K15 right beside it because that was the most convenient place to get it to using less wiring than what it had to control, right? So we're almost at a good stopping point. It's extremely important to learn the symbols used in the reference drawings of your chosen trade. So we're going to be using a lot of symbols. We're going to learn a lot of symbols. PLCs, inside the PLC program, we have very few symbols. In fact, in this class, we'll need to know the symbol for a simulated relay coil, and then of course contacts, and then timers and counters. So this class, we only have time to get through timers and counters as far as learning how to program that. PLC 2, we get into what the computer can do. So everything that we're doing now, except for counters, we can do with relays. Everything that we do, we can do with relays. But a computer can do so much more. A computer can do math. We can't do math with relays. But a computer can do math. We can't do compares if anybody's programming if. We can't do if statements with relays, but we can with computers. So what we do in advanced PLCs is we get into the high level, the higher language, compares, sequencers, trying to think of something. Compares, sequencers, big logic. We'll talk about that. Relay logic, we just do very few numbers of combinations. And computers, though, we can do very, very large binary. It's important to learn the terms used in the language of your trade. So this is a lot of the terminology class too. The problem is PLCs are computers. So that means to really understand these things, you not only have to understand relay logic, you've also got to understand some of the terms that we use in computers, like numbering systems. How many understand binary? How do you understand hexadecimal? How many of you know hexadecimal? Octal. That's the kind of stuff we need to learn, because a lot of things that we deal in PLCs, they're going to be either binary, or it's just like this computer. If you know the binary number system, you could do a heck of a lot more than you could do with what you know how to do. And I'll show you some examples on these computers, and where they actually give you binary information, but they don't give it to you in binary. They give it to you in a base that's easy for us to understand. So this is what we're going to do, guys. We're going to learn a lot of symbols. We're going to learn, well, not many symbols, all the way up through timers and counters. Normally open, normally closed contacts, we'll look at those. Relays, we'll understand inputs and outputs. We won't wire the PLC up in this class. We won't physically wire it, but you'll actually have to draw the way you would wire it. Does that make sense? So you'll have to draw the way you would wire it. So if you ever look in the lab book, just about every lab, it says, how would we make these connections to the PLC? How would we do this? So we'll talk about that. We'll bring one in here. We'll bring several PLCs. In fact, we'll bring the two PLCs that we're primarily going to use in this class. I'll bring them in here. Show you how we connect to them, how we tell our computer to communicate with them, and all kind of neat stuff. Oh, this is pretty interesting. So voltage is measured in volts. This is, you always wonder how they figured this out, but 1 amp. So we measure the speed in amps. Everybody okay? Y'all heard of that before? I mean, you go out and buy a vacuum cleaner, it's now rated in 1 amp. Well, what that is that's an indication of how fast those electrons are moving. And I can always see somebody counting these things. 6.25 times 10 to the 18th electrons moving past a point in a circuit in 1 second. So that's just many electrons. A lot of things. They had it calculated. Here, we're going to talk a little about, we might look at reactants a little bit, especially when we do things. We'll definitely have to understand this, because we need to understand how I can take a push button and hook it up to a PLC. Because the push button, what's required by the circuit? What do we need to have a circuit? We gotta have one. Gotta have a solar. Gotta have a load. We gotta have a load. That switch is not a load. So where's that load at? Well, that load's gotta be inside the PLC, right? Understand that. On an output, the load is no problem, but on the input, we need to understand that, because we'll learn about different ways that we can do input. So we call it syncing and sourcing. We'll learn what that means. Give it some examples. So there's going to be a lot of terminology. In fact, I think there's a glossary on the book. So I don't think we need to look at this. We're not going to do any math in this class. That's American wire gauge. We don't need to look at that. Power we'll come back and talk about later on, just to understand what high voltage is. Okay, last thing we need to look at, guys, is what we call opens and shorts. And then we'll be through. So what is a short? And this is one of the misused. My mom used to say this all the time. She didn't call it a short, she called it a shortage. Something I must have a shortage. But you're in a technical trade class, and just because everybody else, you hear short all the time. Short. It's got a shortage. And odds are it's not a short, because if it's a short, it's going to burn stuff up, right? So if your light don't work, it don't mean it's a short. But that's out here. If you're a technician or you're in the engineering community, you need to learn this term. So when current flows through resistance and it generates heat, and metal gets hot. So where's the short? So a short is a undesirable path for current flow. So that means I have lost control of the current. I still have current flows. That means I've still got a path, but I've lost control of the current. Which decreases the amount of opposition in the circuit, which causes the total current in the circuit. Now that's a short. This is the guy that gives us. It's called a short circuit. So what's a short circuit? Most people don't understand this. A short circuit is somehow your source conductor and your return conductor come in contact with each other. So we've lost the resistance of the load. So the amount of current we get into a circuit, by the way, it mathematically says I in the circuit is equal to V over R. If R goes to 0, what does I go to? So division is subtraction. If you understand, so division, what we do is we'll take the number I'm dividing by, and then I subtract then I'll divide, then I'll do this. Now what we do, and believe it or not, when I first got into microprocessors could not divide. They could do two things. They could add and they could subtract. That's all the microprocessors could do. So how did we make them divide? Well, we had to write a program. So we had to really learn what division was and what multiplication was. So what we would do is we would take the number and we would subtract the second number from it until we generated a bar, which means I've subtracted as many times as I can. So it means I could come up here and I could take 25 and I could divide it by 5. So that's going to be 25 minus 5. What would that give me? 20. Then I'd say 20 minus 5. What would that give me? 15. Then I'd say 15 minus 5. That would give me what? 10. Then I'd say 10 minus 5. That would give me what? 5. Then I'd say 5 minus 5. That would give me 0. And then I'd say 0 minus 5 gives me a bar. So then I would count the number and I'd have 5, and that would be this. How many times can I subtract 0 from a number before I generate a bar? So what's 1 minus 0? What's 1 minus 0? What's 1 minus 0? So any number divided by 0 is infinity. So that's why when you do it on your calculator, it says error, because your calculator can't deal with infinity. Right, you understand? So that means the current technically would try to go to infinity, which is not good. Now it can't, because there's resistance in the wire and there's resistance in the source. But a lot of current's going to flow. It's going to create a lot of heat. I mean, even though my wire might have 1/10 of an ounce, you put 1,000 ounces to 1/10 of an ohm, that's a lot of watt. It causes fire. So short circuits cause fires. These are bad. So any number divided into 0 is 0. Any number divided by 0 is infinity. Unless you say 0 divided by 0. Ask, anybody got Siri on their phone? Ask her what 0 divided by 0.
Wait, we're not.
She says, imagine you got 0 friends. It's pretty cute. So short circuits, anytime we lose the insulation off the wire, we get that and try to make it. So insulation is rated at a certain temperature. If you exceed that temperature, then the insulation could break down, and if it breaks down, then it could, then conductors can break down. Or you can create it by incorrect splicing. Splicing is when we connect two wires together, termination. This is when we bring them in. So that says infinity. Can't go to infinity. Hopefully we got a watt in there. So this is a short. So we get these every once in a while. Anybody ever had one of your light bulbs on your series string go out and take a piece of aluminum foil and put it? You took them right. That's aluminum foil. Of course, then after that, the bulbs blow a little faster because now they're dropping more voltage. This would be a short. So notice I've gone through a load. This would be a short. This would be a short. This is a short circuit. This is boom. This is what gives us problems. So we have insulators. Everybody know what the insulators are for now, right? This is an open circuit. So a short circuit is an undesirable path for current. An open circuit is when we come up and we actually open up one of the leads. We have what we call an open. This is what you create all the time in your house. So that would be an open. So that gives you the ability to turn off a light. So you're creating an open, right? You understand that? And it don't affect any other of your loads. This is an open, this would be an open, this would be an open, that would be what we call an open circuit. So your circuit breaker creates an open circuit. A light switch creates an open, right? Y'all understand the difference? So we have people do this all the time. And then we'll talk a little bit about the difference between AC and DC next class. Y'all got any questions so far? I know some of y'all, we went through breaks. What we try to do, guys, and y'all need to watch me on this. So my fast time is when we're in class. My slow time is when we're in lab. Your fast time is going to be, your slow time is going to be in class. Your fast time is going to be in lab. So we try to take a break every hour. We take a 2-minute break every hour. Why you understand that? So when it gets time to take a break, somebody in class needs to go up. Now I might get through with my thought, right? But we need to do that because I know these lecture classes can get very, very, very boring. Huh? Boring? I'm boring. So very long. So any questions? The PowerPoint slides are up there. What, Charles? Why did you even roll? Now what?
Even roll.
Yeah. You were here when I called Robert.
No.
No, you weren't. No, I didn't. Books. Oh, one more thing before y'all split. Tuition. There's quite a few in here that haven't paid y'all's tuition. Y'all need to get that paid as soon as possible. Probably drop out. We're probably going to drop everybody that hasn't paid their tuition out of class. It doesn't mean we can't add you back. But this year could give you problems with financial aid. If you apply for financial aid and you're having a problem with it, you need to go by financial aid and see if they can basically give you an exemption, which means it will give you more time to get employed. So I hate for some of y'all to drop that. Okay? What's your last name? What? I thought you were here, but now that you remember, I know you were here, but you weren't here when it wrote.
It's a 4th edition for that book.
How much was it?
The book, they have a 4th edition. It's like $135, $38.
So which book did you get? Did you get the old one or the new one?
The new one.